On page 2, we're starting with Bohr models. So as a refresher from what we just went over, what two particles are located inside the nucleus? Inside the nucleus are, if you don't remember, you can flip back to the front page. Protons and neutrons. We abbreviate them inside the nucleus with the symbols P and N. The number of protons will always equal your atomic number. So on your periodic table, your atomic number is, so if we did like carbon, your atomic number would be the one that's at the top. And then your average atomic mass or your molar mass is what's at the bottom. But remember that that number is not your mass number. And then your mass number, this is what we just practiced with the chart on the back of your notes. Your mass number is taken by your number of protons plus your number of neutrons. So I'm going to flip back to the front real quick and I'll come right back. So if you didn't get that, don't worry. When we're looking at this chart, we said that our protons and our neutrons each have a relative mass of 1, and your electrons have a relative mass of 0. That means that when we're taking the mass of an atom, we're not taking into account the electron mass because it's pretty much nothing. So on this page, when we take our mass number, your number of protons plus your number of neutrons, those are both of your mass-having particles, your particles that have a relative mass. And then this is the part that seemed to confuse a lot of you as we were working our way through the chart, is how to find your number of neutrons. So your number of neutrons is taken by your mass number minus number of protons equals number of neutrons. Subtract your mass number minus your number of protons to equal your number of neutrons. It will always be a whole number. You are not rounding this number at any point. You're not using that number. This is an average. It doesn't necessarily mean that it's reflective of what that element or what that atom actually has. And then finally, we're going to put that electrons are located in orbitals surrounding the nucleus. And then this question says how many electrons can fit in each orbital. This is kind of where I walked you through your periodic table, using your energy levels on your periodic table so that you don't have to memorize this. So these numbers correspond to energy levels or orbitals, where in the first energy level, that's anything in the first row on your periodic table, it has a maximum of 2 electrons because I only have 2 boxes in that first row. In my second orbital, my second energy level, I have 1, 2, 3, 4, 5, 6, 7, 8. So that's where that 8 comes from. Then my third orbital, also 8. 1, 2, 3, 4, 5, 6, 7, 8. And then my fourth orbital, that's where I get up to 18 because there's 18 across. And then what about fifth? What would you predict for the fifth orbital if we ever did that? Can you tell how many electrons would be able to fit in your fifth orbital?
5.
Also 18 because it's the same number as in the fourth orbital. So when I ask how many, it's just counting how many boxes straight across. And then the way that we do this is the lower orbital must be full before you start filling higher orbitals, meaning that the first one must have 2 electrons before you start filling the second orbital. So I'm going to zoom this in. We'll do a couple of Bohr model examples and then we'll call it. So if we're drawing a Bohr model for oxygen 17, if it is oxygen, how many protons does it have? 8 every single time, because oxygen on our periodic table is atomic number 8. So 8 protons. Since this is an atom, because there's nothing on here indicating a charge, nothing that says ion, nothing like that, we can assume that it is electrically neutral, which means that my number of electrons will also equal 8. And then another way to write the mass number is like this. So what we practiced on the back was doing like oxygen and 17 up here. So that's one way to represent it as a symbol. But in word format, we write the mass this way. So that 17 represents our mass number. So if my mass number is 17 for this atom of oxygen, how many neutrons would I have? 9. Perfect. So when I draw this, I'm going to put my protons and my neutrons inside the nucleus, and instead of drawing 17 little circles, we're just going to abbreviate them the way that we learned. So 8 protons and 9 neutrons. They'll go in the center. And then the way that we draw our Bohr models, and your kind of like shortcut way to do this efficiently and effectively every time, is that if I look for oxygen on my periodic table, what is the energy level that oxygen is situated in? Is it in energy level 1, energy level 2, energy level 3, 4, 5? Oxygen is in energy level 2. So what that translates to for us in Bohr models is that we would have 2 rings around the nucleus. Yeah? 2 rings around the nucleus because oxygen is in energy level 2. And then oxygen has 8 electrons, and those 8 electrons are going to be housed between those 2 energy levels, but a specific number in each one. So we always start in energy level 1, the one closest to the nucleus, that can hold a maximum of 2 electrons. So we put them on opposite sides. If you're packing up, please wait just a second. So my electrons in the first energy level, or first orbital, go to the opposite sides. I've drawn 2. And then I still need to add 6 more to get to my 8 total electrons. So 1, 2, 3, 4, 5, 6. Which makes sense because if I'm reading this Bohr model, this shows me there are 2 electrons in energy level 1, which I have according to my periodic table. And for oxygen specifically, in energy level 2, I have 1, 2, 3, 4, 5, 6 electrons. Wait, we're not done. Stop packing up. Since a lot of you have had no exposure to chemistry before, you may or may not have heard of the term valence electrons. Valence electrons are simply outermost electrons, meaning in the furthest shell from nucleus. So outermost electrons. When we refer to valence electrons, that is what we'll talk about. So for this example, my valence shell is energy level 2. It's that second ring. How many total electrons are in the second ring for this example? 6. Most atoms need 8 valence electrons to have a full valence shell. And when we talk about things being stable, that means full valence shell. So zoom that out, let you finish copying it, and then once you have this, you're free to pack up and you still have plenty of time.